John Wager, would you like to step forward, please? John has already addressed us at a previous meeting, about Charles Redrup, and gave us a bit of an eye-opener on that. Today he's going to be talking about Stanley Hooker. A lot of you may say yourself, who was Stanley Hooker? Well, there's a book called Not Much of an Engineer. I read it about 18 months ago, and it blew me over. It really was well worth the read, and John has had a good read and analysed it, and being an engineer himself who worked in the same area, he's well qualified to tell us something about it.
Thank you, Brian. I want to start with also some words of thanks to Brian Herman. It was some time ago when Brian suggested that the members here might like to learn a little bit more about Stanley Hooker, and particularly from Stanley's autobiographical book, which is entitled, erroneously in my mind, Not Much of an Engineer. And I plan to correct that. When I started building a PowerPoint that you'll see on the screen, again, Brian stepped in and he's substantially improved it, particularly with photographs of aircraft from Brian's extensive collection. So thank you, Brian. Those of you who were here at that earlier meeting might remember Charles Redrup. He was an outstanding mechanical engineer. He spent his lifetime designing internal combustion engines. He was a competent precision machinist. He had his home workshop. But he was an unassuming perfectionist. No headlines. In fact, when I spoke, I was about the only person in the room who'd ever heard of Charles Redrup. But we managed to introduce him at that meeting. But for this meeting, we meet Stanley Hooker. Here he is. And I hope to show you that he really is a competent engineer, even though he never achieved an engineering degree. In his 77 years, he achieved much. In terms of aircraft, we usually associate a Hurricane with its designer, Sidney Cam, Spitfire with designer Reg Mitchell, the Lancaster with Avro and Roy Chadwick, the Mosquito with de Havillands. But all of these aircraft were powered by the Merlin. Unfortunately for us, the Merlin was continuously being improved in its performance. And the key person in that improvement process was Stanley. He joined Rolls Royce in 1938. He had never before seen an aero engine. Within months, he'd added 30% more power to the Merlin. Later, he turned the Whittle turbojet into a production engine. He was responsible for most modern British aero engines. He developed engines for the Concorde and the Harrier. He masterminded the RB211 recovery program after the debacle, and he received a knighthood in 1974. He's quite an engineer. Well, no, he wasn't. He was a brilliant mathematician, by his own words, with no engineering degree. He was, in the words of his colleagues, he was the first to give credit to others when things went right, but also the first to assume the blame when things went wrong. Almost by accident, he became one of the world's most brilliant engineers. He was an expert in supersonic airflow. His analysis of flow in the superchargers kept the Merlin ahead of the Germans. He introduced Rolls-Royce to Sir Frank Whittle. He designed the Neen, which in his own words were licensed to America and, quote, foolishly sold to the Russians. He promoted vectored thrust, and the Pegasus was a success story for the Harrier. Going back to his early days, at school, in his own words, he made uninspiring progress, but he was very interested in physics and mathematics. He gained a place at Imperial College, and he studied hydrodynamics and von Karman vortices. Now, von Karman was a colleague of his. Von Karman also was a mathematician who studied the three-dimensional flow of fluids, oil, gas, water. I think the most common example of a von Karman vortex we've all seen. If we have a stream that's flowing smoothly, and if that stream then meets a round rock, which my left hand represents, as the flow reaches that stream and passes it, it has an eddy profile. I think we've all seen this, and it's seeable, it's photographable, but mathematically in 3 dimensions it's extremely difficult to model. And Hooker did, and von Karman did. In 1932 he entered Oxford, in his own words, as a callow, gauche young man, but he left, and I won't recount his personal comments as to how he became mature and rounded. His personality changed, I think, for the better. In 1935, he was working with the Admiralty in the Scientific Research Department. He studied the range and the speed and the flight of shells and rockets. And most interestingly, he worked on the weight and the size of a rocket to reach Berlin. In 1937, he sought a job at Rolls Royce in the engineering department. He was interviewed by Ernest Hives, the then Rolls Royce works manager. Now, Hives had no doubt read Hooker's CV, and his question was, what is a Karman vortex street? Well, unfortunately, Hooker replied not as an engineer but as a mathematician. And he got the response, "You're not much of an engineer, are you?" Which became the title of his book. Fortunately, Hives then asked for more information and for some of his research, and his next comment was, "When can you start?" So before we proceed, I think it's important to have a flashback here, and I think it's a most serious one. In the early 1930s, Heinkel in Germany developed the HE-70. It was a fast aircraft. It had an elliptical wing, one each side, and retractable undercarriage. Rolls-Royce at that time wanted a modern aircraft in which to develop the Kestrel engine. So, and wait for this, 4 Kestrel engines were exchanged for one HE-70. And the exclamation marks I've added are because the Germans used the Kestrel to develop the ME-109. And this is a model of the one that became a British aircraft, the HE-70. So that in 1939, when Hooker was with Rolls-Royce, his first task was to improve the output of the Merlin to compete with the ME-109. He worked on the supercharger at the amazing speed of 28,000 revs a minute. Something to imagine. He improved its efficiency by 15%. Even though he had never previously seen a supercharger. He did it all by maths. Hooker worked on airflow, the intake ducts, oil cooling, fuel lines, and the biggest advance was 2 superchargers in line with an intercooler. And he got 1,000 horsepower out of the Merlin at 30,000 feet. In 1939, Hooker, the mathematician, had never seen a machine shop or lines of machine tools, inspection departments, assembly lines, or test beds. Things that have been so familiar to production engineers and mechanical engineers for years. His approach was the mathematics first, and then practical production and development. And so we have the Merlin, which is a beautiful thing, and at the rear end of it we have the 2 superchargers with their intercooler. Think of the contribution of each of those 4 aircraft to the war effort, and think what improvement they would have gained from the improvement in performance of each of their Merlin engines. for the intercooler, for the superchargers, and that was necessary because when you compress air, obviously it's heated up. Anyone who's pumped up a bicycle tyre with enthusiasm will remember. You need an intercooler. Well, Farnborough produced a copper matrix. And the Farnborough representative proudly brought this prototype matrix to a meeting with Rolls Royce. And the Farnborough rep said, "Oh, it's robust. You can jump on it." So Hooker said, "Show me." Well, the rep jumped and flattened it. And Hooker said, "Never mind. Tell them that clumsy idiot Hooker did it." Oh, the Merlin carburettor had a big problem, and it may be known to some of you, not firsthand, I hope, because in the early 1940s, when a Spitfire endeavoured a sudden dive, the 2G minus 2G upset the carburation and sometimes caused an engine flame out. And this posed a bit of a problem because the ME109 by that time was fuel injected. The solution came through this lady. Her name is Beatrice Schilling, and as you can see, one of her great hobbies was riding TT motorbikes. You can see her here astride her Norton 500 and a big smile on her face. But she was also a member of the Royal Aircraft Establishment. And she solved that Merlin problem with the carburettor with a simple disc with a small hole in the middle. It controlled the flow, it solved the problem. And it was known by pilots and Rolls-Royce people as Miss Schilling's orifice. Ernest Hives became Lord Hives, and Hooker wrote of him, Hives was with Rolls-Royce during World War I, and with this experience he was able to lead Rolls-Royce into aero engine design and production in World War II. He said that Hives was the right man at the right time in the right place to bring our country to victory in the air. Well, those words, right man, right time, right place, I believe describes Hooker. In 1940, Hooker met Frank Whittle. Hooker wasn't an immediate convert to the jet engine because he said, it's only got 800 pounds of thrust. Well, it was put to him, try this comparison. The thrust of a jet engine with the horsepower of an internal combustion engine. The Spitfire with 1,000 horsepower at 300 miles an hour, coupled with the non-efficiency of its propeller, produces a thrust of 840 pounds. The jet engine, 800 pounds thrust. The Spitfire, even with the improved Merlin, 840 pounds. So Hooker thought, think of a jet engine with 1,000 pounds of thrust. The strong advantage of the jet is the internal combustion engine has only one power stroke per 2 revolutions. The jet provides continuous power. Hooker became converted. And Hooker set about converting others. The question put to him was, did the jet work by sucking or blowing? Well, he solved that question by using an air-filled balloon to show blowing. Well, one day, prior to a lecture, he realized that he hadn't blown up the balloon. So he retreated to a toilet cubicle to blow up the balloon. But he blew with such enthusiasm that it burst. And there was a silence, broken only by a plaintive voice from the next cubicle. Are you all right? A much more serious note, in 1941, the UK and the US governments instructed Whittle to give design specs and a prototype engine to General Electric USA. Significant. In 1942, Rolls-Royce took over the manufacture of Whittle jets from Rover, who initially had the contract. Hooker became the chief engineer for the Rolls Royce jet program. The jet program was moved to Barnslwick in Lancashire, about 100 miles north of Derby. In 1944, the Welland engine was fitted to the Gloucester Meteor. In 1944, Hooker was invited to the US. General Electric, by then, had already a jet engine of 4,000 pounds thrust. Hooker decided, we'll design a Whittle-type engine by Rolls-Royce of 5,000 pounds, and that was the Neen. Interestingly, the Neen turned out to be perhaps the most manufactured jet engine in the world, but perhaps sadly not manufactured to that quantity in England. It was manufactured in Russia, as we've learned, in America, in China, and in France. And it was used in Australia, of course. In 1942, I worked briefly at Commonwealth Aircraft in Melbourne, and I was observing the thrust of a Neen on an engine test bed that was developed to assess the performance of the Australian-built Neens. Here's the Gloucester Meteor with the Derwent. The Derwent was a scaled-down Neen, which in itself is quite a feat. To scale down a design of anything is something worth tackling. Hooker said it's a sobering thought that the two great current competitors of Rolls-Royce, which today have the bulk of the world's aviation business, Pratt & Whitney and General Electric, both started with British engines. You remember they were given to General Arnold in 1941, before the US was a participant in the war. Rolls-Royce then developed to the Axial Engines, and the Avon, there's one in section, is an axial through flow engine. This is the intake. There's a 12-stage compressor leading into the combustion chambers and then driving the turbines, obviously to power the compressor, but also to give some 10,000 pounds of thrust. The Avon was fitted to the Canberra, the Valiant, the Hunter, the Scimitar. And many others. After the war, 1947, the Avon and its manufacturing was moved from Barnslwick, where Hooker, you remember, was chief engineer of the turbine engines, back to Rolls-Royce headquarters at Derby. Hooker pressed Lord Howes, as he then was, on an earlier promise that Hooker would become chief engineer at Derby, and this was not agreed. So in September 1948, somewhat in a huff, Hooker left Rolls-Royce after 9 years and joined the Bristol Engine Company. 1949, Hooker became chief engineer of Bristol Engine Division and further developed the Proteus engine. It was a turboprop developing 3,200 shaft horsepower and still with an 800-pound jet thrust. It was a very interesting engine. I like to look on it as a folded-up engine. This is the pointy end, there's the gearbox, and this is the propeller mounting. But the air intake is well aft, and the air is drawn in and induced into a 12-stage compressor, and then it's turned 180 degrees into the combustion chambers, 8 off, where it drives a 3-stage turbine. The first 2 turbine stages drive a hollow shaft which is connected to and drives the compressor, and the 3rd stage drives an internal shaft inside the hollow shaft to the gearbox and the prop. You can see it better with this animation. There's the intake of cold air, which becomes rather warm when it's compressed, and then the combustion leading to the first 2 stages of the turbine. And then the 3rd turbine drives through the middle, the hollow the middle of the hollow shaft, the drive to the gearbox. Now remember that this is transmitting 3,200 shaft horsepower. Just imagine the torque on that shaft and imagine the twist if the pilot presumes to push the throttle just too urgently forward. The Proteus was intended for the Brabazon and also the Princess flying boat. The Brabazon. Look at that tail fin. And the Princess. Magnificent creation. And the Britannia. The Britannia was equipped with a Proteus, but a sad crash of ALRX altered this. The problem was located in straight spur gears in the reduction box. Straight spur gears kinematically transmit even torque and turning, but the force on an individual tooth is not even. It increases and decreases, and that torque fluctuation, looked at in another direction, leads to fatigue input and fatigue failure, and that can be amended by changing the straight spur gears to helicals. The helical gear still transmits continuous and smooth kinematics, but it has a force transmission that's less severe. So the gearbox was redesigned as helical, and the Proteus development continued. From 1949, the development of design moved to the Olympus with some nominal 16,000 pound thrust. This is the Olympus, and this is the cross section. It was the first two-speed turbojet because it used the hollow tube drive in addition to the central shaft drive to arrange that each compressor spool had its own turbine. So each stage, each compressor could be designed by Hooker to have its own peak efficiency, resulting in up to 40,000 pounds thrust. And the Olympus was used in the Vulcan bomber, which gave 25 years naval service. The Canberra, which achieved a world altitude record of 66,000 feet. It also powered, or four of them powered, the Concorde. Four of them powered the warships, and they were used for land power generation. The Avro Vulcan, the English Electric Canberra. I was fortunate when I undertook my graduate apprenticeship in Preston, England, to see the Canberra still being built in Preston. The Concorde. And that led to the Pegasus. Now the Pegasus was quite a different engine. The Pegasus was designed jointly by Hawker, designing the airframe, and Bristol designing the engine itself. So the jump jet was a combined design team. The Pegasus engine was designed with the high pressure and the low pressure spools counter-rotating. You might remember when we spoke about Redrup at an earlier meeting that in World War I, those aircraft that were powered with a rotary engine had to put up with the gyroscopic effect of this massive rotating engine during aerobatics, and that proved disastrous. In fact, you might remember that I spoke in that previous address of Redrup having developed a counter-rotating engine. It had two props, and it was reaction-free. You might remember I had a line drawing of him sitting on an imaginary chair, sitting comfortably with a balanced thrust. But if the gyroscopic effect in World War I was severe, it became even more important in the need to have a stable hovercraft. It was quite important. Another matter that was included in the design was to have puffer jets fore and aft and on the wingtips. This idea of having 4 puffer jets was used in some of the earlier flying bedsteads, but those earlier ones were controlled automatically, and that didn't help the pilots. A pilot likes to feel what's happening and feel that he can control what's happening. And when it was automatic, the pilot didn't quite know where he was or who was doing it. So the control for the Pegasus was part of the secret. Now, I don't have time to speak in detail about the Pegasus, just to say that there was a 2-stage induction, and that led to these 4 ducted jets. The first 2 were known as the cold jets because air from the compressor was bled down into the first 2. So they were the cold jets. And then the compressed air, the remaining compressed air, was passed into the combustion chamber to then fire and feed these 2 stern jets. Obviously, there was the need to have these all 4 operating simultaneously. And that was achieved by, again, bleeding a little air and a gearbox, and transmitting that via a motorcycle chain on each of these ducts. So they all moved simultaneously. It was an amazing design. There's much more about it, but that's perhaps for another story. You have all seen the Harrier, and you've seen its performance. And here you see the duct pointing down. In 1960, a lot went on in the British aircraft world. In the engine world, there was an amalgamation of Bristol, Armstrong Siddeley, de Havilland and Blackburn, and they became Bristol Siddeley engines, BSEL. And the airframe was a combination of Bristol, Vickers Armstrong, English Electric and Hunting under the British Aircraft BAC heading. Rolls Royce in 1966 made a successful bid for BSEL, $63.6 million. Hooker then sought a seat on the Rolls Royce board, and that was refused. In 1967, perhaps also in a huff, Hooker retired from Bristol, but he was retained as a consultant. And now we come to the RB211. While Hooker was with Bristol, the RB211 was under development by Rolls Royce. The B in RB211 is for Barnsley, where Hooker originally established the jet engine factory. The RB211 has 3 advantages. It's a 3-shaft, 3-spool engine. I described earlier how it's possible to get maximum efficiency by having individual drives to each of the stages. The 3-shaft, the 3rd shaft, is a dedicated drive to the fan. As we know, the RB211 is a high bypass ratio engine. There's a very large fan driven by a dedicated turbine. And the result is the fan provides some 75% of the thrust. So the engine looks a little like this. This is the main jet cycle of compression, combustion and jet, and this is the fan, which gives almost a cylindrical shield of high pressure cold air around the envelope. The RB211 had a very early problem. Those fan blades failed the bird strike test. In 1970, Rolls Royce was in financial difficulty, bankruptcy. the government took over, changed the board, and changed top management of Rolls Royce. Hooker was invited back as technical director. He was told, it's good to have you back, but you cost us $63.6 million. What he did was at least threefold. The first thing he did was to change the engineering staff approach. I haven't had a chance to describe him as a person and how his personality enabled the development of the Neen and the Avon. But he had a way with people and worked well with a team. Technically, he replaced the carbon fibre blades with titanium. The titanium blades were heavier, and that incurred a performance penalty, but he overcame that by making the turbines more efficient by initiating lost wax casting. That enabled internal cooling channels within the turbine blades, and that improved the output more than the titanium was a negative effect. So he thus improved the design of the RB211 to £50,000, still with 75% from the fan. And there was a successful contract that saved Rolls-Royce with Lockheed. And you can see how the 211 has evolved. This is the Rolls-Royce Trent, the 900. Now, Hooker, in later life, 65 through to 75, as a consultant, made many visits overseas. To Bucharest, Romania had an interest in manufacturing the Viper engine. So there were top-level meetings. There was the then chair of Rolls-Royce, Sir Kenneth Keith, and Hooker, and the then President Ceausescu. Romania gained a license to manufacture the Viper. Hooker was quite influential. He also made, in 1972, an overseas visit to China. That was the first visit for foreigners to China. They were shown a Russian-built Neen. You remember that the Neen was foolishly, effectively given to the Russians. But there was a constraint on the gift, and the constraint was that the Russian Neen was to be used simply for commercial aircraft. But being Russians, they didn't worry much about that, and they re-engineered, they copied the Neen for military use. When Hooker was shown in China, the Russian-built Neen, he said, "Oh, it's an excellent copy. They've even copied my mistakes." They were also shown a US-built General Electric J47. And Hooker said, "How did you get that?" And the Chinese said, "Oh, it fell from heaven." Now, in 1972, Hooker and his colleagues, in 1972, that's 40 years ago, the Chinese engine factory had 10,000 employees. Think how many employees they have now. And it's not so much a wonder how they were able to produce a stealth aircraft to challenge the Americans. After involvement of the UK government in 1972, China gained a license to build the Rolls Royce Spey 202, and Hooker made many subsequent visits to China. In January 1974, he received his knighthood. In 1978, he made his last farewell visit to the Rolls Royce factory in Derby. And just as a summary, before I conclude, let's see what happened, has happened, to the jet engine horsepower equivalent pattern. You remember the first Whittle jet with 800 pounds was equivalent to a Spitfire 1,000 horsepower. The Concorde cruising per engine developed 36,000 horsepower, and the Concorde just cruising with 4 engines 144,000 horsepower. 144,000 horsepower. What's the horsepower of your motor? And then 4 Olympus in the aircraft carrier, HMS Illustrious, down-rated for marine use, still 120,000 horsepower. HMS Illustrious had a top speed of about 30 knots. I mean, water skiing on the Swan River, if you got 30 knots, you're amazed. An aircraft carrier. These are the engines that Hooker has been involved in, or had been. The Merlin, the Welland, the Derwent, the Clyde, the Neame, the Trent, that's the early version of the Trent, the Avon, the Proteus, remember the folded up one, the Orion, the Olympus, the Orpheus, the Pegasus, and the RB211. His influence on each was significant. This shows Hooker towards the end of his career with the significant painting of the Spitfire. And this one shows him, besides the painting that was commissioned by Rolls Royce, to commend him. This is the book from which I've been speaking, Not Much of an Engineer, by Sir Stanley Hooker. He says, maybe I'm not much of an engineer, but I think he's an excellent engineer. And if you do too, well, let's thank him. And thank you.